this opportunity. This is different than mine down there. So I'm going to talk a little bit about the background for the mechanical to digital governor conversion that we did at Stanislaus Powerhouse. Stanislaus Powerhouse is on the Middle Fork of the Stanislaus River, about 100 miles southeast of here, near a town called Angels Camp. You may have heard of that. Mark Twain made Angels Camp famous with his celebrated frog of, or jumping frog of Calaveras County. I wasn't there then. But Stanislaus is a 91 megawatt unit, 6 needle jet vertical unit. It's capable of about 800 CFS. The water supply for this unit is around 550 CFS, so this unit is used for ISO control and is moved all over the place. It's actually one of the largest single unit plants in the PG&E hydro network. Until recently, the speed control was managed with a 1960s Woodward governor, a mechanical governor. This governor utilized over 450 feet of steel cable for the needle restoring, needle feedback, almost a ton of counterweights and countless shivs and pulleys. Kind of looked like an erector set that I built in 3rd grade. As with anything that's this age, we had normal wear and tear issues. It was difficult to keep this unit tuned. We had excessive hunting. It was difficult to parallel at times. And of course, with all these hydraulics, we had multiple oil leaks all the time. This cabinet was continually impacted by a continual oil film. As I mentioned, one of the major issues in this plant was that it's used for ISO load following. They would make easily over 100 megawatt set point changes in a day, and they could be as much as 30 to 40, 50 megawatts at a time. And the way that would operate, the way that was handled, the ISO would send an analog set point to our control center. That would turn around and send a digital pulses to the RTU at the powerhouse. That in turn operated the interposing relays and then operated the speed adjust motor. So the speed adjust motor was in constant flux, just being bumped up and down. And as a result, the speed adjust motors lasted about 18 months and usually failed about 2 weeks before our scheduled outage, so I had to deal with a forced outage just in time. Also, the RTU relays would also fail. They would only last about a year, so those were on an annual replacement. In addition to all these issues, PG&E also recognized that this unit was run at the lower end, down below 40 megawatts quite a bit of the time. And so we were losing efficiency because we were at the lower end of the efficiency curve for a 6 needle jet. So we started looking at the possibility of running the unit in pairs of needles, and so we came up with the 2-4-6 scheme. And so in 1990, we installed the Woodward 517 controller, and the problem with this is that it had solenoid valves that would just force one pair of needles closed, so we didn't have independent control of those needles. So if we would go into say a ramping situation where we'd go from 15 up to 80 megawatts, the first 2 needles would start opening following the deflector cam, but as it went through the first threshold for the 2 and 4 needle threshold, the second set of needles would start opening, but they're opening up at their maximum rate, while the first 2 needles are opening up at the rate defined by the deflector cam. And as they got close to the position of the other needles, then we'd get a megawatt spike. And then of course that would happen again when the second threshold was passed, and the second, or the pairs 1 and 5 would open, and you would get a second spike. So the curve, the megawatt load curve going from 15 up to 80 was very bumpy, and it was very unstable. in addition to that, when we used to control the megawatt set point, we were pulsing the speed adjust motor so that it never really knew where we were trying to go. It was just kept pulsing up until it got there. And so we didn't have the ability to tell it how many needles it needed to have to get to that particular location. So it would have to transition through the whole 246 instead of just going directly, start opening all 6 needles. And then the last item was that there was always, because of all the cable restoring and all the weights, there was always a lot of slop in the system, so that the speed adjust set point would never match the ISO set point. And so there was a constant battle. It was always in a hunting situation. And we fought that for a couple of years and finally abandoned the 517 and the 246 concept. Then in the early 2000s, we started seriously looking at a digital conversion. So we started looking at the digital governor conversion so that we could start eliminating some of the mechanical problems that we were having, the increasing maintenance costs, the frequent calibration requirements, the constant hunting, the difficulty paralleling. It wouldn't even hold load very accurately, and the constant replacement of all the relays and speed adjust motors. So that's when we made contact with American Governor, and they started helping us out, and that's where I'm going to give it to Matt, tell you what he did.
Oh, well, obviously Matt works with me. He's a project manager, who was a project manager for this job as well as many other jobs. And
okay, let's keep going. So in, I believe, 2008 through 2009, we engineered and installed this system, and I'll talk a little bit about what components were in the system and what the gains were. So the biggest advantages of the digital conversion are the replacement of the 450 feet of cable and 2 tons of weight with modern electro-hydraulic controls. This allows for precise servo motor control, allows for servo motor control to be self-calibrated by the software, and additionally, we're going to have direct set point communication from the California ISO to the governor, and get rid of that several step communication link with analog signals and set point raise and lower commands. So this is the inside of the control cabinet. We used Allen Bradley Control Logic PLC, and because of the critical load following nature of Stanislaus, we went with a rather thorough redundancy configuration. We have a full redundancy for PLCs, including power supplies, CPUs, and the I/O modules, using a redundancy configuration that we developed with PG&E and have used on several plants, including Kern Canyon and Helms Pump Storage. We have redundant power supplies, redundant HMIs, redundant servo motor feedback on the deflectors, but we do not have redundant servo motor feedback on the needles because the needles themselves are redundant. Also critical to the system is DNP communication directly to SCADA and more or less directly to the California ISO for set point communication. This is the front of the cabinet. So you may know Carl from Stanislaus. He is operating the HMI, which is a drop-in replacement cabinet to where the old controls used to reside. You have HMI indication, some basic set point controls through operator switches, and analog and digital readouts of your servo motor position and tachometer. This is the inside the hydraulic control cabinet. You have your deflector controls using modern Bosch proportional valves with LVDT feedback, and a very similar configuration on each of the 6 needles. This right here is where the vast majority of the gains in converting to a digital governor are, especially on a unit like this, where before the governor was controlling the deflectors, which was then controlling the master needle, which was then controlling the 5 slave needles. A lot of slop and between those several steps, resulting in the poor needle control, which resulted in the poor megawatt control and the poor ability to transition between needles. We can now individually control each needle very precisely, and that's really where all the gains are. And just to give you a comparison, this is again what the old system looked like. So you can see how much simpler, cleaner, and more direct the control is. So to performance, this is a 1 hour time slot of the old mechanical governor, with the red line being the set point from the ISO, and the green line being the governor, the actual megawatts out of the unit. And what I want to point out are the lags in response to set point changes, but more importantly, the hunting you're going to see around here, here, and here, where you'll see the set point is actually deviating away, or the actual megawatts are deviating away from the set point, and sometimes in an uncontrolled manner. Also, you can see here a significant lag in following set point. Now, with the new governor control, you are still going to see some lag due to the natural rate that the unit can load up on, but that lag has been decreased. What you'll also see is no areas where the set point, where the megawatts are not moving towards the set point. They're always tracking as accurately as possible. And that, again, is limited by the rate of change of the servo motor stroke. So, how do we get smooth and consistent megawatt output? What we're looking at here is, this is a test, this is actual test data from commissioning of manually ramping up the megawatt set point from no load to full load with needle sequencing active. The blue line is the operator set point being ramped up in steps. The green line is an internal set point used to ensure consistent loading. And then the red solid line are the actual megawatts. And what I want you to notice is the more or less general smoothness and linearity of that ramp rate. Now what you're looking at in the dashed lines are the 3 needle pairs. The blue would be the first and fourth needle, green would be the second and fifth needle, and red would be the third and sixth needle. So the first needle pair is ramped up until the set point crosses the transition boundary, at which point the second pair would ramp up at a fixed rate, and the first pair would control on its own under PID control to maintain constant flow changes through the needles, and therefore constant megawatts. And again on the next transition. What you'll also notice is that the rate of change of 1 needle pair moving alone versus the rate of change of 2 needle pairs and 3 needle pairs. The 3 needles is at 1/3 the rate of 1 needle, and 2 needles at half the rate, so that you do again get that consistent loading. One other feature that you're not going to see on this chart is if you were running at around 10 megawatts and you put in a set point of 80 or 90, it would immediately transition to 6 needles because it knows that that's where you need to be. And that alleviates some of the long loading concerns they have with the other unit. So needle sequencing allowed for a 3% local efficiency gain at low loads, and a theoretical 2% total operating efficiency based on how they operate Stanislaus. Something they were not able to do, and really interesting to see, is to set up flow monitoring on the unit and track unit operation over maybe a 1-month period with needle sequencing on and off and see what these gains actually were. But as many of you are aware, that's a difficult test to set up, and especially when the unit's up and running and there's no complaints. So real quick, some of the other features that were obtained with the digital conversion, we now, through the ability to independently control the deflectors and the needles, we can control isolated loads. There is the ability to control a roughly 12 megawatt load in the event of losing all 215 kV lines. And that's through something called water wasting, where the needles are positioned roughly where they need to be for that 12 megawatt load, and the deflectors are the controlling mechanism. Deflectors being much faster than needles are much better suited to control speed. Additionally, lower maintenance costs of this equipment due to the, well, mostly from the not needing to do calibration as frequently, and parts, pins, linkages not wearing out. The elimination of the oil leaks is a welcome benefit. And in the future, if any expandability is required, such as doing 4-bay level control or after-bay level control or down-base control for any kind of cascaded river management, that would easily be added to the system because of the digital nature. So with that, how are we in time? I'm going to invite Mark back up real quick to talk about some of the lessons learned with this project.
One of the things on this, the old governor, we used GST 68 turbine oil, and the recommendation was made that we should switch to hydraulic oil because of the tighter tolerances of the new control valves. We also performed a hot flush on the entire system. As a result of that, we did not have a single hydraulic related problem during commissioning and haven't since. So that was a strong benefit. Once again, during the design stage, making sure that we had operations input on how this was going to be designed. The controls are a completely different animal for these guys, and so they're not used to working with an HMI. They don't know what kind of data is available, so getting them in the loop early was a big issue. And the last one, we had a little issue about a year after commissioning where one of the control parameters had changed, and we don't know how it changed, and it resulted in the needles actually closed on a unit trip, but the sensing didn't see that the needles had closed, and so we motored the unit for a few hours. And so Matt and I have been talking about that and changing the software so that it tracks those changes and allows us to see when the change was made and even potentially alarms when the changes are made. So that's basically it.
Are there any questions for Mark